Hello, I'm Joao Palotti from the Earkick team. In this presentation today, you see how sometimes renotating data might be worth it, as better data can lead to better speech recognition models. For those who don't know Earkick yet, we are a mental health app with the goal to support mental health in real time. For that, we measure mental health in different modalities, like speech, video, and text. Today, let's talk about speech recognition part of our system. To create our voice-based emotion recognition model, we use datasets that we internally created at Earkick and community datasets. And while investigating the different community datasets, we faced problems and issues that we wanted to share with you. For example, there are these two groups of datasets, the in the wild and the acted datasets. Given the natural in the wild setting of our app, should we only use the in the wild datasets or should we combine them somehow? While investigating the largest of the in the wild datasets, CMU mosaic, we found this factor of a magnitude for one emotion. But how should we use this? Should we use the default threshold that everybody uses or should we use another threshold? And we wanted to investigate this in this presentation. We also had some philosophical questions like, are all the emotions equal? Should surprise be harder to classify than happiness? Let's see. To study these data sets and try to answer our questions, we decided to re-annotate 1% of each one of the 4 data sets below. We followed the same CMU mosaic labeling procedures and re-annotated with 3 team members from 3 different cultures, 3 different continents, with no time pressure at all. As in the wild datasets, we re-annotate CMU mosaic and fwild too. As active datasets, we use Trimady and RevDes. All 4 datasets are extensively used by the research community. To annotate this data, we created a label studio instance as shown below. For each one of the emotions, the annotators follow the same procedure as the original CMU mosaic creators and mapped how much of that emotion would be in the audio from 0 to 3, for none to extremely. Let's see, for example, here. The annotator might have classified the happiness of this audio as moderate, or as little, or as none. Here there are 3 different opinions from our annotators, and we average them all to get the final score of 0.33. There are a total of 10 label possibilities listed below. Now with the final numbers in hand, we could start correlating numbers. We highlight from our experiments that the overall correlation is just medium, showing how hard the emotion recognition task is, even for us humans. Among the emotions, happiness and anger show the highest agreement. On the other extreme, fear had the lowest correlation between our annotations and the original ones from CMU mosaic. This finding is interesting and needs to be further studied. One of the experiments that we are most excited about is controlling the threshold for the binary classification and checking how much agreement each threshold will have. The peak of this main agreement is when the threshold is 0.23 and the kappa value is 0.30. This is shown in the dashed blue line below. What we are actually proposing is experimenting with this new threshold. In other words, what would happen? What would be the effect on the machine learning models if we move the threshold from greater than 0 to greater than 0.23? Before doing the actual machine learning experiments, we took advantage of this multi-label confusion matrix visualization below to see the difference between the original assessments and our new assessments. Here we provide you with 3 different plots for the 3 different thresholds that we wanted to study. This confusion matrix usually allows us, for example, to understand what are the pair of emotions that are most often misclassified. But what we are really interested in today is to see the numbers in the diagonal lines. Inside each cell, we have the percentage of agreement for a given emotion and a number of samples for each case. When we increase this threshold, the number of samples of each emotion decreases. However, at the same time that we moved to the right, the noise of the weakly classified instances decreases, and that's why the percentage in each cell increases. Finally, we ran machine learning experiments with these three different thresholds. For that, we used a state-of-the-art architecture based on pre-trained Herbert-based transformer models. We extracted features from the audio samples and classified them into some classes. It could be 0 to 6 emotional different states for each audio sample. In the top table, we show that increasing the threshold in the test set can make the task easier, as we increase the agreement and only select the very easy ones to classify. This explains why the machine learning results improve. However, what we are more interested today is the results in the bottom table. Here we show that training a model with our proposed threshold provides huge gains when transferring learning from CMU mosaic datasets to other datasets. To recap, we saw today that emotion classification task is a challenge task, even for humans. We learned that not all emotions are equal. Some emotions have higher agreement than others. This disagreement can cause confusion to machine learning models, and our study showed that some of this noise can be eliminated by using a slightly higher threshold than the usual one. Due to the time limit, some topics from the paper were not presented today, and we invite you to read our full paper. Finally, there are some limitations in our work, including the fact that we re-annotating all the samples only listening to the audio, not using the video, not the transcribed text associated with each sample. That's it. Thank you very much for your attention and attending this talk. At Earkick, we have awesome projects and we are planning to have internship positions available soon. So please keep in touch and download our app. Thanks.